Whoa.
Whoa, pressure's on.
Absolutely. Well, Sir Sagi, would you like to start us off?
Well, I'm not sure. We got some high quality results. I was working with Joe mostly for the past, like, I don't know, 3 to 4 days to finalize SCG abstract. So we were basically summarizing what our efforts to develop our DC code to serve our GWB project. So we developed the 1D, well, we had the 2D and 3D, so we developed the 1D code. Thanks, Prise. I actually used your Hankel transform as well for our DC.
Oh, okay.
And yeah, I was actually thinking about using your code, but there was a bit of accuracy issue if I set the 0 frequency. So in the large offset, the accuracy was fine, but at the very near offset, there was some problem with accuracy. Anyway, so that was sort of the reason why I had to revamp this propagation matrix stuff. But anyway, so that was one new development. And Joe worked really hard to improve the efficiency of our 2D and 3D code. So I think Joe can mention that later. But anyway, now it's actually I'm pretty satisfied. So we can run relatively large size 2D code in, like, I don't know, a few minutes. And also you can run the same 2D line in 3D about the same time. So yeah, I thought that's great. Joe, can you explain what you've done?
Yeah, essentially, I think I talked about it a little bit before, but it just goes through the survey and to find all of the unique pole-pole combinations. So every, like, dipole, Wenner-Schlumberger pole-dipole, they can all be reduced down to linear combinations of pole-pole electrodes. And furthermore, those pole-pole electrodes can be arbitrarily switched due to reciprocity, right? So it kind of goes through and then finds all of the unique pole sources, which therefore reduces the amount of matrix solution it needs to do for, like, the forward JVAC and J-transpose back operations to just the number of unique source electrodes instead of the number of sources. So even though you could, like, for these examples that we had before, we had dipole or Wenner-Schlumberger type surveys where there could be 1,500 data points, and each of those data points had a different combination had a different dipole source. So even though there are only 72 electrodes, you could calculate the entire survey using 71 sources. So
that's actually a huge improvement. If you think about, like, if you just did the, like, a kind of naive approach, you have thousands of sources, even for, like, a relatively small size 2D DC survey. So you need to store all the fields of 1,000 sources, which could be pretty expensive. So we had memory problem for a 2D problem, which was insane.
But are all these sources on the same depth level and the receivers?
Yes, but it doesn't have to be. It doesn't have to be. So
okay.
The survey that we've dealt with was mostly like a surface-based DC survey, but the code is not limited to. You can put the source and receiver everywhere, except for the error layer.
Yeah, just because if they are all on the same depth, then you could save massively time by just doing one survey.
That's when you're computing with analytic solution. Pre-say, I guess.
You're in 3D.
Yes.
Yeah, right. Okay.
Either, like, we're solving PD.
No, just because you mentioned the Hankel transform. Okay.
That's for 1D. Yes.
Yeah,
So I used that benefit when I was computing the Hankel transform.
Regarding the accuracy issue, I don't think it's I think it's a setting issue, not a computation numerical issue. If you could send me once a small example of what you were running and what went wrong, that would be interesting to know. Yeah.
I'm actually curious because
I have in the settings there are some values set to a minimum, like offset and frequency. But if under known conditions you can change these settings.
Wait, yeah, it's a little bit of segue, but I was actually curious that the minimum filter that you have is of just the 51 points. So I think that for the DC, we don't even need the 51 points.
Okay.
So I was wondering, can you even design like a smaller filters, like 20 points?
Yes, for this we have this design package we published last year. So if you would have a very specific problem, we could try to design a very short filter.
Oh, yeah, that'll be interesting. So anyway, what we were talking about was the solution is in it's like a Bessel function. So you need to somehow transform that into a real domain. So Dieter developed the Henkel transform code that I was using. So we were just talking about, and then the number of filter like if you got more filters, it increases your computation cost. So if you can have minimum number of filters, that'll increase your speed. So that's what we were talking about.
Yeah, we can look into that. So, because in this publication, they mentioned that for huge inversions, and you are talking about huge inversions, it might actually be faster to do first a loop with a quick filter design for the problem at hand, and then use an as short filter as possible. So that was
To clarify, we haven't used for our 3D code, but like that was actually purely 1D inversion.
But in the 3D, you're not in the wave number. Yeah, that's fine.
And Sagi, for the abstract, is there anything you need from anyone right now, or is it just like, close to the final read through, or?
Yeah, on my end, I'm done.
Okay.
So anyone can have a final input. That'll be great. So we ended up bumping up the floor, Doug, so that the undulating feature. I think it was because of the sort of the noisy data at the larger offset. So by bumping up the floor, we could remove like both those like undulating features.
Oh.
Now like all 3D, all like a 3 inversion are quite consistent, as well as 3D.
Okay.
So, and in 3D, I think we can actually like better recognize those dry zones within the aquifer. So I emphasized in that part in the paper because like that's what you would have missed if you just used the 1D inversion. So
okay. So you've actually changed quite a bit then since the last read.
Correct. Yeah. So the results are quite changed.
Okay. I will read that immediately after getting off this.
Okay.
Okay.
Well, thanks, Sagi. I see Devin, you've typed some things in. Would you like to go next?
Yeah, so I finished up the 1D MT code and got a little bit of a review from Joe, and it works great. So, I mean, I could do a 30-second screen share where I run it. I don't know if anyone has the time, but just to show you what I mean.
Sure, if you want to do a quick demo, that'd be great.
So let me, one sec. Okay, so you guys should be seeing a little Jupyter notebook here. So I'll just restart and run all. And so I'm inverting, I think it's 21 frequencies and like 21 layers for a smooth inversion. And yeah, it usually finishes in about, here we go, like 8 seconds, 10 seconds. So that's pretty quick. And yeah, so we've got some apparent resistivities. You can model apparent resistivity, or you can model impedances. So we've just got a more resistive block in a more conductive half space. Here's our apparent resistivity curve, so we're sensitive to all that. And yeah, go through the inversion, and this is a model that we recover. And there's our how well our predicted data matches the observed data. So Yeah, we're able to effectively invert impedance data and the apparent resistivities. And I found that I did an analytic computation of the sensitivities. I did the math, and it actually runs faster. So I'm glad that I put in all that work, and it led to good things. But yeah, I think maybe if somebody wanted to review it at some point, I think it's pretty much ready to be merged in. Joe gave me some feedback, which was very useful. But when I have time, I'm thinking about how I can look at pseudo 3D.
So I know I brought it up earlier. Did you get a chance to switch from like the exponentials and things?
No, I haven't done that yet. So that's actually, I should write that down because
I do think it's like it can like those like just playing with your code. I definitely saw stability issues with, like I said, with large thicknesses and small conductivities and things. Definitely
Thibault,
happens in codes.
Thibault worked on that quite a bit, right, Thibault?
We have a 1T MD semi-analytic for the forward modeling.
Yeah, there was one.
Yeah.
But yeah,
Yeah,
I think
so-
Like you use it for the GeoSci lab. We for comparing the inversion in the leading edge.
was it a propagator matrix solution or was it
Yeah,
like a
yeah, you were
discretized solution?
no, you were propagating matrices from down to up.
Okay. Yeah, the one that I found in where I looked in SimPEG was the 1D, like the discretized 1D that you find from Eldad's book.
Okay, so I think it might be in GeoAna. Look
Oh.
there. Like I remember doing a lot of work to bring it in a usable format.
So there is some of these, like they're in the SimPEG codes. They're in the NS near surface EM natural source utils. And there's an analytic 1D utils in there. There's solutions for the EH fields that use that upgoing, downgoing approach.
Yeah, I did see that, and that
And
was.
then there's also the analytic impedance code that uses the recursive formula for just to get in the impedances.
Oh, really? Sorry, what folder? What's the file path for that?
So it's in natural source, utils, and then analytic 1D.
Mm.
And Thibault, actually, maybe if you could find a link to just where your implementation is and drop it in the notes, that might be a useful resource for
Yeah, that's what I'm looking at right now.
Sure.
Like I just don't remember where that is, to be honest. So we'll have to dig down.
That's fine. Because I think you had implemented permeability and complex conductivity in that too, right?
Yes.
Okay.
Mm. For the forward problem.
It was only the forward. Yeah, like it was only like, okay, here is like a layered model of the Earth. Get me the empty result for EH and impedance. And I was also doing like some tricks of normalizing the response so that if you had like, because like if you were starting too low, for example, and you were putting like very low conductivity or stuff like that, like your signal can blow up and you were getting like massive errors due to rounding issues. And so I had a lot of tricks that it worked in pretty much in every situation, even if you were throwing something kind of like crazy at the bottom.
All right, so there's definitely some work to do because I didn't really consider this.
Yeah, so that kind of solution definitely happens with the upgoing and downgoing type approach. It doesn't happen in the impedance approach because of it uses hyperbolic tangent functions to do it. So it's much more numerically stable if you're just concerned about impedances, which is all you need for the 1D inversion anyway.
Yeah, what I was doing was kind of like a normalizing at each layer so that you were not blowing things up.
Yeah, I would take a look at those two.
Yeah, because you'll. Okay, Yeah, I can look at some of that stuff.
Awesome. Dom, do you have any updates?
I started going back to the DC, the simulation DC part. I was running some tests for Nick, one with one of his data set, and even with well, I guess no, we're not using it yet. Basically, the mini survey that Joe implemented, we don't have it currently with the DAS hookup. And even then, when we have a very large survey with many sources, our bottleneck right now is the right-hand side and the fields. Right, we still have to build those giant dense matrices. So what I was thinking yesterday, and I might try to implement it this week, is if it would be possible to just call fields for specific sources, right? So instead of doing the whole thing all at once, if we could block our right-hand sides and our sources, and even ask only for one, for instance, if you want the fields for a single source. So that way we'll be able to limit how much memory we're using at every time. So I might give it a shot. I don't know if people have an opinion on this, or I've tried already.
Like why don't you actually do they have really 3D survey?
Yeah, it's a complex survey, and yeah.
So breaking that apart to a different domain is pretty hard. Is that what's happening?
You mean do like a tiled approach?
Yeah. Because usually what I saw from even the DS data, which is pretty 3D, it's pretty localized. You have limited number of electrodes that you can use for a single shot, so they basically move they're like a big electrodes array from here. So it's still quite localized. So I thought basically just do a tiling you could save a lot. I thought, because if you can say reduce your a simulation domain at, let's say, factor of 5, that should be pretty durable, I guess.
Yeah, that's one way to do it. Yeah, for sure. I just don't understand why, when we're doing fields, that why do we doing all the sources? Why don't we just be able to just say, give me the fields for that source, right? If you have already a full survey, it's kind of hardwired right now that we're forming all the right-hand sides and all the sources at once. But I think it would be kind of nice if we could have the option to pick which one we want to do.
Right.
Yeah.
And that way we could block it, even when we call the data, right? We could just ask, compute these blocks of sources and give me the data only for these guys, instead of having to do the whole thing at once.
Oh, I see. Are you thinking about storing it in in a hard drive and basically loading, or are you thinking about computing that on the fly?
You could just loop at that point, right? Because right now the memory cost is that it's a dense matrix of n cell by n sources. So if you have thousands of sources and you're in the 100,000 to million cells, those are two massive matrices that you need to store in memory.
Correct.
When really what we want to do is compute data at the end of the inversion, so we could for loop through blocks of it without having to store the whole thing at once, right? So then the only bottleneck is AM, which is not a big deal if we start doing tiling after that.
Right. Yep, that sounds good.
That's a cool idea, Dom, and I think actually that might even provide us a bit more flexibility with how we parallelize things too down the line, is be able to just take chunks of the sources, even if we're not doing the tiling, but still be able to actually parallelize that way.
I think it's a more long-term benefit to do it, because we can propagate the same thing to all simulations,
Mm-hmm.
rather than having to just do patches for DC only, right?
Right.
Yeah.
Can you, so basically we're computing that once and storing it at the moment. That's our strategy, right?
Fields, yeah.
No, I was thinking about just the right-hand side. Field is changing. The field is changing every iteration for DC.
Okay, but both, yeah, right-hand side and fields, yeah.
Right-hand side is not changing. So
No, it's not, but we're storing it. We're holding it to memory.
Right. So right-hand side, so our strategy now is basically compute once in the beginning and basically store it. But the problem is the storage, right? So
Yeah.
that's huge. It can be huge. And so
It's as big as the fields.
so what's your strategy? Like I wasn't exactly sure.
Right-hand side is really, at least for the DC, right-hand side is like extremely cheap to form, right? Because it's a bunch of zeros with like 1 or 2 cells that have non-zeros on it. So it should be a sparse matrix at first. And then second, to form it is insanely easy. So we should just form it on demand, basically.
Okay, so just do it on the fly.
On the fly. Because for the inversion, if we're gonna store sensitivities, we only need it for at the beginning of forming J, and for at the end of the inversion, we only need it to compute the predicted. So we don't really need to hold it in memory this whole time. It will be kind of basically a trade-off between how fast you want to compute versus how much memory you want to use. So we would have that
right.
flexibility basically.
Right. So, but that seems like an easy solution because doing it on the fly, because we can just put a flag.
Yeah.
Either you store or just do it on the fly. That seems an easy solution. But
yeah, I was looking at my memory consumption. Just forming the right-hand side, I was ramping to gigs, and then I looked at the matrix, and there's nothing in it. We're basically storing tons of zeros and holding those zeros in memory for the entire time.
Right. I'll take a look because I think I used the sparse matrix when I was forming. It's only when that's actually when that's multiplied to AN that I think that changes into. Then I'll double check because I think in the beginning we set that as a sparse matrix.
Yeah, in simulation right now it's dense for sure. Yeah. It's just a numpy zero matrix.
So it comes down to the thing that the source term dense is as big as the fields object.
Yeah, it does. Yeah.
So we could change the solvers. Some of them have in place operations, like the Paradiso can do the solution in place, which is an option. I don't think some of the more basic solvers have that as an option. SciPy's conjugate gradient might, but I don't know. I don't think so.
So what is solution in place?
So it'll overwrite the right-hand side vector with the solution.
Okay.
So that's a factor 2 basically would be saving up, right?
And it's if you're going to be if you're going to be doing something with the fields object anyway, and you're storing the fields object somewhere, you're already going to be using that memory anyway. So it could be an option for some of those solvers that we could take advantage of.
Right. Then we probably need to change the current structure because all the right-hand each, I think it's each source object. So we probably need to store somewhere in a different place, I guess. Or we can have the same structure but point to where it's stored.
Well, I think, Sagi, it depends if you want to store it as what we're storing is because the sources can each keep track of their own source vector right now, I believe is how this is working, at least in the EM side of things. So that each source can keep track of its own vector that is then used to construct the right-hand side. So I don't think for the most place, at least in the EM codes, we're not storing the right-hand side, but each source is storing its vector. But we could easily have it not actually store that and have it computed on the fly each time.
So I guess that's the same thing as storing the whole right-hand side then, right?
Yeah, but I think I wouldn't be surprised if the memory footprint in Python is actually bigger, potentially, because each object is storing an array rather than just storing one matrix. So I wouldn't be surprised if, like, conceptually it's the same, but in practice it could be different. But I don't know. Okay, well, Tom, I'll be really curious to hear what you play around with and come up with. That's super cool. Any other things that you wanted to bring up?
Nope, not on my side. Not that's it.
Thibaut.
Yeah. Last 2 days I was helping Sarah to get some visualization stuff going with for her project, and I need to create an issue. I just haven't done it yet. So we succeeded, and I see that she just posted a picture on the Viz channel. So it looks pretty cool. So we succeeded, but it was not as straightforward as it could have been. Or it just like, yeah, between the so there were issues at 2 levels. So like we cannot plot vector field yet on quad 3 mesh. I had to interpolate on a tensor mesh, which was fine. But I think the biggest thing, and I had to go back to the GeoSci lab for that, is that with the DC code for the 2.5D, if you call any other field than phi, if you call E or G for the field object, it fails. You get an error message. So I actually had to like compute phi everywhere and then compute the E and G field by hand, and then by that hand computation bring it back to a tensor mesh. So there was like quite a few steps involved from going from a survey and problems, etc., to visualizing the field.
So do we not have E, J, and the charge density implemented in the DC field object?
Well, for DC, yes, 3D and 2D, but for the 2.5D, I was getting error message.
I see.
For the 2.5D code, you have to call like fields to space method, like that method on that field object first, because it has to do the operation of transforming them from the the wave number domain to the space domain.
Yeah, but all I'm saying is like like when you take that field object and you send us the syntax for that Geo, fortunately, but like when you're writing phi, it's fine, but you're supposed to be able to write E or G or charges, but it fails. That's all I'm saying. Like, so I think there is except if I was really doing something wrong that I didn't see, I think there might be something with the 2.5D there that failed. I will send an issue when I got time to document it properly. But yeah, every other field than phi was failing on the field object for 2.5D.
Yeah, that's expected.
Yeah. Okay.
Yeah, we didn't implement that. So the actually definition of fields in 2.5D, it's in the wave number domain. So like implementation wise, it's working. But what you want is transformed current density in an actual space domain. So that one we don't have it. We only have for phi.
It is there. So what you have to do is you have to call this. That's for the 2.5D code. You have to do that simulation.fields. And then there's another operation that you can do that calls fields to space on that simulation object that implements that transform and then stores it back as a normal DC field.
Yeah, because like even when you call the field object, I realize that like when you call the field object with phi, it actually gives you a vector that's kind of like mesh size by number of spatial Fourier transforms. So like 16 in that case. So we had like it was giving a matrices the size of like mesh number of cells by number of frequencies.
Yep.
So like that's fine. But when I was putting E instead of phi, I got literally an error message saying that the argument were not implemented.
Yes, so there's no E and J there. Sorry.
Yeah. That's what I'm saying. So like we get something because she just wanted like a visualization of the current on her mesh, like to show what's the source is like and what the current look like. So it was just for visualization, but it was like, yeah, I'm just saying that with the tree mesh and the 2.5D, it was not as easy as like, oh, call the E field and then plot slice a vector field. You had to pretty much like do a lot of things by hand. That's all I wanted to bring up.
Yeah, Thibaut, if you can make an issue, we could put something together like that you could do that.
Or at least be a little bit more clear about what you should do with the 2.5D fields.
Yeah.
Yeah, that sounds like a great opportunity for an example that I think would be useful. Cool, thanks, Thibaut.
Otherwise, the 2.5D works great. I love it. It's like in terms of like forward modeling and inversion. It was just like, oh, we wanted to access the field and plot it.
We'll make it happen.
Well, it happened, but manually.
Excellent. Thanks, Thibaut. John, do you have any updates?
Yeah, I got pretty sick of making GUIs or working on the GUI stuff last week. So I kind of dived into a bit of the DC again and the MT. Actually, I was starting to do exactly what you guys are talking about, the DC problem there. So I've split the fields up so that you can calculate them all at once, or you can do it by frequency. I'm making it so it stores an X array instead of a dictionary for each solution. I haven't got around to testing it, but I want to see if just calculating it on the fly, storing it as like a delayed X array, and then compute just what field you want at that time. So I'm just working on that right now. Then the DC, I just went back and did some of Joe's suggestions there. I was trying to form those big sparse matrices ahead of time instead of doing the transform every time from a NumPy to that. And then I put all those other get A deriv, get row deriv, row deriv into one big delayed function so that it's just, because they got to be called in sequence anyways. And that's about it. But yeah, mostly the MT. I'm trying to see if what's the difference if we just calculate fields on the fly.
Oh, super cool. Well, I'm looking forward to chatting through that maybe in more detail tomorrow when we do the MT meeting. I think that's going to be, I'm excited to see what you've been doing.
So you've changed the fields. The fields is no longer the dictionary. It's an XArray. Is that what you did?
That's what I was working on this morning. I'm going to try that out and then delay that X array, or even if we store the X array, I don't know. I'll probably end up trying it all, but whatever one I get to first there.
On a note, I think for the MT, we probably need to consider like using an iterative solver, because like that's actually much more making sense in terms of parallelization. So if you can figure out like a relatively good iterative solver that can solve Maxwell's equation, I think that'll bump up a lot. Like you can actually solve a much larger problem.
It could be a really good case for a multi-grid solution.
Something like that.
Excellent. Thanks, John. Any other things you want to bring up?
That's it for now. Yeah.
All right. Joe.
I think I've gone through everything that I had to do with chatting with other people.
Fair enough. Dieter, do you have any updates you'd like to share?
Yeah, what I've been working on. Mostly I try to push the thing that we have here, these CSEM model comparisons. We try to make a paper of custom and PetGem. I don't know if you have heard of those. PetGem is a project from the Barcelona Supercomputing Center. Custom is from Leibniz Institute of Applied Geophysics in Germany. And SimPEG and my code, which are all codes that can do CSEM modeling. And we kind of want to show a bit the similarities and differences of these codes and do some 3D comparisons, mainly because of, well, you always compare it to analytical solution and 1D solutions, but if you have a 3D code, you would like to have also some comparisons with 3D models. So that's what we try to do. And it was a bit on and off for a while, and now I really try to get it over the edge. So I hope by next week I can put it to Raphael, which is the guy from Custom. And then, yeah, we go from there.
So I owe you a simulation there. I will get working on that.
Dieter, do you have like I don't know, like really a typical model, like a seismic for Mamusi model or something like that? I don't know. I'm not sure EM people have that, but do you have something like that model that people use to compare their codes and stuff?
There was last year. Well, the first thing I did was this SEG SALT model from the 90s.
Okay.
Adapted to a marine case. What you now use is this Marlim R3D model. I don't know if you have heard of that.
No, what was it?
Marlim R3D. I'll send you the publications. It's a realistic 3D resistivity model offshore Brazil. It was created by some Brazilians. They took seismic velocity. They actually followed some stuff I did in my PhD, which was cool. They took seismic velocities and well logs and all the information they had and created a 3D resistivity model.
Oh, cool.
And published that open source in the first publication. And then they used Schlumberger EMGS software to compute 3D CSEM results and published that open source. It's all on Zenodo. And just now they published MT data from that same data set. So they extended the model for magnetotellurics and they published MT data.
That's
it's
awesome.
A huge real world resistivity model for those sort of things.
What is the size of the, like, is that it's like a voxel model?
90 millions, I think, the original.
19 or 90?
90.
90 million. Wow,
yeah,
shoot, that's big.
And that's just the core model. Then the whole computational is then bigger, but then they also coarsened it. I forgot how, but I think, yeah, with a couple of dozen million cells, they run their forward simulations.
Is there topography on this model?
Yes, there are a couple of layers. There is a bathymetry. Yeah.
But the upper surface. So everything is done in the water, is it?
It's offshore. Yep, it's offshore.
Okay.
Yeah. But then you could remove the water, and then you have a onshore. Well, then you don't have the data to compare to. Yeah.
Or you can pretend that as topography.
Yes.
Consider it to see as an air.
No, yeah, but their model is offshore Brazil. Yeah. So that was one, and the other thing is with my code, I tried to integrate it more in the workflow of the consortium in which I'm involved at the moment. So it's currently trying to integrate it into joint inversions of gravity and magnetic data, that sort of thing. So there I'm looking into the gradient at the moment. And I actually want to ask, how does SimPEG do gradients in 3D?
Are you talking about potential fields?
No, electromagnetics, full waveform.
What do you mean gradient?
Like
gradient?
For an inversion or the Jacobian, if you want, or how do you do
Oh,
it?
I see.
Yeah, we compute that all analytically. And so like the method JVec, for example, we've basically gone through and done the derivation of basically what are all the matrix vector products that give us J times a vector and J transpose times a vector.
Yeah, okay.
Well,
And what cost does that come then, at one forward model, or?
It's multiple. Sorry, Joe, go ahead.
Generally, each JVec and J transpose vec operation individually, if you have the fields pre-computed, then it's the cost of one forward operation generally.
Yeah.
Yeah, but usually more than that. It's usually
A little
more
bit
expensive than forward.
Yeah. Okay. But it's different from the adjoint state method, or is it similar? No, it's just analytical.
I think it's actually exactly same. That
Yeah.
J, like a J transpose vector is is an adjoint problem. So
Yeah. Okay.
if you actually write it down in math, it's exactly same.
Ah, okay. Yeah, that's what I'm using, but I don't have it implemented analytically. I just get the residual source and then do a backfill propagation.
Yeah,
That's
I
how
think
you say
what
it's the same.
Lindsay meant analytically, I think it is same as what you're doing. I believe.
Ah.
So
yeah.
it's like
Okay.
that analytic means like it's not finite difference, but we're deriving that that adjoint problem, adjoint solution in a discretized space.
Good.
Yeah, thanks for clarifying, Saki.
Yeah, that's it.
Cool. Well, thanks for joining us. It's good to have you.
Well, yeah. Thanks for shifting.
Absolutely.
Getting up early.
Well, it's not too bad. It's good for us. Doug, do you have any updates you'd like to share?
Nope, not really. We're kind of consumed here with SCG abstracts, which are due in a few hours. But I want to do a real shout out to Joe and Sagi for the improvements that they've done to the DC code. Amazing speed up in performance and the reduction of memory and the speed. That is really going to make a difference as far as people actually using the code. So yeah, 2 thumbs up.
Excellent. Perfect. Okay, well, yeah, in terms of my updates, I guess, been working on SEG abstracts. In addition to the Myanmar ones, I also have one for machine learning on the classifying UXO from EM data, and that one's basically done. I think I dropped the link in last time, which should be the same. Yeah, I can drop it in the notes again. But if anyone reads through and has any feedback or ideas, I mean, this is one that I would like to eventually turn into a paper. So I'd be curious to get any input and thoughts. Yeah,
maybe about this, if you want to ping Jan Willem. He joined SimPEG a couple of weeks ago, so he's a master student here. He's working with Fugro, and he's looking into this topic, not with machine learning, but just with coding.
Oh,
so
cool.
Maybe he would be interested to read it and give some feedback, or yeah.
That would be great. Could you ping me with his name whenever you have a second, and I'd be happy to do that. Yeah, and then so tomorrow we'll do a chat about MT and natural sources. I think there might be a couple people from Berkeley who just drop in to say hello, who are involved on sort of the Jupyter side of things, just to kind of get a sense of what we're working on. But yeah, we can use that as a chance to start to sketch out some development plans and figure out how to sort of divide and conquer to make some progress there. Yeah.
Dieter, can I ask one quick question? So you mentioned that the model was 90 million cells, right? But the actual size of the domain that they are solving using the EM or MT code was about 10 million cells. Is that about it?
I'll check for you. I'll come back in 5 minutes with all those dimensions. And I'll write them down. I have them. And
that's sort of like a kind of usual size that you guys all deal with for offshore problem. I'm just kind of curious about the size of the problem. How
they did it probably in a bit unusual way. They had a massive grid, a very regular grid of receivers, and then also a regular grid of sources. So they computed a huge model, right? Which is probably good for a synthetic survey. So they put it on a cluster and let it run. You could do that by a line-by-line basis, like what we do for the comparison here in our paper. We just pick one inline and one broadside line, and then you don't need the whole model, because then you limit your survey massively. I don't think you would do a CSEM survey of that size, at least not in the beginning. Yeah.
Okay.
But I do think that the likes of EMGS, they have quite massive models, definitely in the dozens of millions, I would think.
10 million-ish.
But then also mostly iterative solvers and not direct solvers.
Okay.
Okay.
Thank you.
Okay. Does anyone have any other closing thoughts, questions? Devin, you're muted. If you would.
There you go. Yeah, not related to SimPEG, but I was hoping that maybe Doug and possibly Lindsay could stick around after for finalizing the overview case history, or sorry, the overview abstract.
Yep. That sounds.
And I invited Ren in so that he can be a part of it, or they can be a part of it.
All right. Sounds good.
Quick question. Yes. So
Yeah.
did you agree to do it once a month at that time, or is it going to be every week at that time and I join in, or what is the?
I think I'm good with every week at this time. Does that work for everyone else?
Yeah, it's just easier. Keep it that way.
Yeah.
Cool.
So
Cool.
welcome to come anytime.
Yeah. Thanks.
Excellent. Perfect. Okay. See everyone. I'll stop the recording here and then we can chat about abstracts.
Yeah.
Have a good week. Bye.
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 Yeah.
Bye, guys. Thanks, Dieter. Nice to see you.